How you doing? I'm Mr. Rose, and today we're going to tackle a energy question, which is going to introduce the concept of a differential mass unit. So the question I actually have set up comes from our textbook. It is Young and Freeman's University Physics, 13th edition, and the question we're doing is number 61. So here we have the problem set up. The given parameters are, we have some bar, it's a uniform bar that, the mass is uniformly distributed in the bar of length L. They tell us the length is 2 meters. They tell us the mass is 12 kilograms. And they give us 5 revolutions in 3 seconds. So they want to know what's the kinetic energy of the bar. And the bar is, since it's revolving 5 revolutions in 3 seconds, it's revolving about the end. So this bar is going to make kind of a big circle of diameter, say 2L, twice the length of the bar. Now, when we know kinetic energy, just start as kinetic energy equals 1/2 mv squared. This formula that we've used for, a long time at this point is the kinetic energy of a particle. We only talk about particles moving pretty much at this point. Now, this bar is not a particle. This bar is many, many, many particles, and specifically, if it's not moving in a linear fashion, it's moving in this circular fashion, each part of the bar is moving with a different velocity. So what do I mean by that? If I redraw my picture, my bar, here, like so. Now I'm going to extend that bar such that this is the plane that it's rotating around. So this bar, the way that I've drawn it, is now rotating in this fashion. So every point on this bar, if I look at this small section, that's going to make some circle. Okay, there we go. Some circular motion. Excuse my very poor circle. Some type of circular motion. Now, that section of the bar is going to move with the same rotational speed as, say, that section of the bar. But the tangential speed, or linear speed that we know, the velocity here, v, is going to be bigger than its velocity there, because it's a much smaller circle, right? So if I want to know its kinetic energy, and again, this is some linear form, I need to relate it to the velocities of those pieces. So how do I do that? Because I know that, well, let's see, it's going at a constant speed of 5 revolutions per second, so that gives us a period right there, right? The first thing I could solve, not given information, is the period, which is just 3 seconds and 5 revolutions. So that comes out to 6 over 10, 0.6 seconds. So the time it takes for this piece and that piece to get around is just 0.6 seconds, but this distance, this pink circle, is much smaller than this blue circle. So how do I find that distance? Well, we know that the circumference of a circle is 2 pi r. So I can really say that that constant speed, even though I'm blaming on velocity, we know it's a constant speed, not an actual velocity. Its tangential velocity, or speed, is just 2 pi r over t. So we're going to come back to that, specifically this r. Now, we've known circumference for a really long time. But we have to remember that this r is really just the distance. It is the distance from the center to some point, right? It's like an x or a y distance. Now, let's get back to my kinetic energy formula. I can also talk about, now that if I know this velocity, that this very small mass, right, that mass is moving with a different speed than that pink mass, which means, technically speaking, this section of the bar, the blue section, has a greater kinetic energy than that section of the bar, the pink section. So what we need to do is we need to find the kinetic energy of every single piece in this bar as it travels around that circle. every single piece, kind of summing up all of those pieces. When we're talking about summing up all of those pieces, things should go off in your head of, I must be talking about antiderivatives or integration. So instead of this one big mass, I'm going to change my kinetic energy formula to 1/2 some very small piece of mass that I'm going to call dm. That is a differential mass unit, a very, very small mass. That mass, that mass, that mass, that mass, that mass, all of those masses times what I know is v squared. Now, this is where things are going to get a little bit hairy or confusing because of notation. From here to here, that'd be radius r. From here to the blue piece, radius r. From here to any piece would be radius r. I don't want to be in terms of r. I want to use general forms. So right now, I'm going to say this is the same thing, and this should be easy. Velocity in a circle, 2 pi times x divided by t, where x is going to be that radius r, right? So if I have, let's see, I know they gave us L of 2 meters. If this pink section is 1 meter away, then obviously my 2 pi r, that'd be 2 times pi times 1 divided by 0.6, I'd be able to find that velocity. Just like I'd be able to find the blue velocity if it would say 1.5 meters away. So we haven't done anything except for replace a general r for our circumference for an x. I'm going to plug this in. Kinetic energy, 1/2. I'm going to put my very small, again, I'm just looking for the kinetic energy of that one piece. And now my velocity is going to be, let's go back to that, times 2 pi x over t, and that whole thing is squared. Now, since I said we're summing up all the pieces, right? And again, this is one bar, this is spot 1, that's spot 2, don't get confused. We're really only looking at one piece of this. I want to sum up all my pieces again, so that implies that we're going to need to do some antiderivative, some integration. Now, where am I integrating? I'm integrating from this section of the bar to that section of the bar. So I'm going to integrate all the way through from 0, and I'm going to call that L. Length L, the whole length of my bar. Or what that is a distance piece, right? It is differentiating about some distance. Now, even though this is 0 to L, I'm talking general terms. If I wanted to, since I know my terms, I can say that I'm looking at the kinetic energy, antiderivative from 0. I know my bar is 2 meters. That's my length of 1/2 times my differential mass unit times 2 pi x divided by t. That whole thing is squared. Now, this is great to know, but we have some issues. This length requirement, or my distance requirement, means I need to differentiate about some distance. This is differentiating about a mass. And I know I have a mass and a distance dependence. So what exactly is that dm? Well, dm, again, is any one of these small pieces in here, right? This is a dm. That could be my dm. A very small mass inside that whole bar. So I'm going to set up a proportional relationship, a differential mass proportional relationship. I'm going to say that my mass element, as compared to any, again, I'm antiderivative, I'm summing up all the pieces about some x distance, is equal to the entire mass of my bar, m, divided by the entire length of my bar, L. Which means I can now, and again, this L is our unit of length. If I now want to be very, very careful and consistent, this is specific for Sorry, computer's not plugged in. It almost went out. This is specific for this exact piece. I don't know why I drew that line there. If I want to be very, very, very specific, very general, I would essentially say not mass per L, because again, that's just to this bar. General terms, I would say my mass unit to my differential unit is equal to the entire mass of the bar times any x, any length of the bar. Doesn't matter what bar I have, that's always going to be true. So, if I want to do this now, I'm going to put everything together. I'm going to say the kinetic energy is equal to the antiderivative from general terms, I'm going to say, from 0 all the way to whatever that x is. In this case, it's just 2 meters. 1/2 times dm, well, we can see my dm. dm, I need to sub in, and I want it to be in terms that I can integrate with. So dm is equal to m over the entire thing, dx. So I'm just going to put that in now. Times m divided by the entire length of the bar times, close that, times dx, that's where I'm integrating about. Then I'm going to multiply that by the distance of my bar, right? So it's going to be the distance or the velocity, 2 pi any x from here to here, from there to there, from there to there, from there to there, divided by t. That whole thing is squared. Now I'm hopeful that this is making a little bit of sense here. Now what we can do is we need to pull out every constant. Now let me explain a little bit why our antiderivatives need to match. If, this is a little sidebar, when I take a derivative or an antiderivative, I can only talk about things that, the direction that I'm integrating in or summing things up. In other words, if I had a very simple, say, antiderivative of x with respect to y, right? And we know that the x direction is this way. We know that up and down is my y direction. Well, that means this x has nothing to do with summing all the pieces up in the y direction. So this x essentially acts like a constant. There's no issue with going up and down. So what we're going to do with that is this would just come outside of my antiderivative. And if I'm integrating from 0 to y, I would have then the antiderivative, x times the antiderivative of dy, which we know would just come out to be xy. So if they don't match, if I left this as that dm in a length unit, that's a constant. And that's not going to help us because I know as I change my position on this bar, I don't know if you can see that anymore, as I change the position of this bar, I know that the velocities are different, which is why we can't do it in that sense. We need always to have our antiderivatives match. And in this case, now I have this dx here, I have an x there, and that makes sense. Because as I move up and down my bar, my velocities are changed. The velocity and the energy is dependent on that. So I get to pull out all of these constants. I get to say the kinetic energy is equal to, well, let's see, my 1/2 is a constant. My mass of the bar is a constant, the total mass. The total length of the bar is a constant. dx, that's what I'm taking the antiderivative about. The 2 pi is a constant. So this is 4 pi squared. I'm going to pull that out. 4 pi squared is a constant. The t is a constant. They told me that. Divided by t squared is a constant. I'm just clearly bringing my squared piece in there. Now, all of that is just something that can't change. From the antiderivative, from 0 to the length of my bar, which I called big X up here. big X, which is, again, our capital X, or our length, that's just 2 meters according to our parameter, of x squared dx. And this is simple calculus from this point. When I do this, all of those things stay. K is equal to 1/2. That didn't change. The L didn't change. 4 pi squared over t squared times x cubed over 3 from 0 to 2 meters for the entire length of my bar. Now, when I plug all those things in, again, if we're not familiar with this, when we're plugging this in, it would be this whole thing times x cubed over 3, which would be 2 cubed over 3, minus 0 cubed over 3 from the top to the bottom, that minus that. And obviously the zeros are going to go away. We should come out to, I believe, 3,000 joules of kinetic energy. But to be honest, I don't remember if that calculation is exact. Okay, quick insert to this. I actually have no idea what this is going to look like because I've never just inserted before. I didn't want to just say, oh, I think this is it. And that's wrong. If you plug all this in, let's go get some room. Actually, I can do it right here. Let's get some room here. I would have 1/2. Instead of going to this 2 meters, I'm going to just put it in terms of variables for a moment. 1/2 m divided by L, 4 pi squared over t squared from L cubed over 3. And again, that is from 0. Instead of the 2 meters, instead of putting numbers in right away, I'm going from 0 to L. And then you'll notice I can lose that L, and that's going to be L squared. So now I would have, really wish I was writing in pencil, 1/2 m over nothing, I just put an n there, times 4 pi squared over t squared times L squared over 3. And again, that 0, we plug that in, that's going to go away. This does not come close to 3,000. If you do this calculation, it comes out to 877, a little more than that, 877 joules. So, again, I just couldn't leave it and say, oh, I think it's 3,000. No, definitely not. 877 joules should be your answer. Now, that's all I have for you to this point. Again, feel free to like, click, or subscribe. But since I just kind of shoved this little excerpt into the whole video, it'll look weird. My bad. Make sure to comment and shoot, make fun of me for all I care. That'll make things fun. Talk to you all later. Bye. This problem so slowly is, again, to start to understand this differential mass relationship and the fact that when I take derivatives or antiderivatives, we always need to match. We're pretty good with derivatives now, right? Like if I said the derivative with respect to time of 5, what's that doing? That's not doing anything for me. So we're getting better at derivatives. The derivative with respect to time of 5 would just be nothing, 0. There's nothing to take a derivative of. Kind of the same thing. This is a constant compared to y. Go back up here. dm is a constant compared to x. But we know it's really not. What was, again, this differential mass unit depends on a length or position of the bar. So we exploit that knowledge so we can do simple calculus. I hope this was helpful for you. Feel free to throw out some questions. Be sure, if you're watching this on YouTube, to like, comment, and definitely subscribe. That's all I have for you right now. I will see you folks next time.